So, welcome everyone. This is sixth week, and let's see what is done in this week, and then we will solve some simple questions. Okay. Okay. So this week, sixth week, uh, minimal polynomial and characteristic polynomial of a linear operator. This was discussed, and then Cayley-Hamilton theorem, and after that, invariant subspaces. Okay. So first of all, I will recall what is done in this week. Then we'll go to solving questions. Okay. Okay. So first of all, if he is a linear operator, okay, let me write like this. Let let P be a linear operator. Okay, all vector spaces I'm uh, talking are finite dimension. This is our finite dimension. Okay, okay, T be a linear operator on V. Then there exists polynomial f x in Fx such that Fp is equal to 0. Okay, so how to show this? This was done like by saying t power 0, which is identity, t power n square, and add one more, t power. Okay, this is consisting of n square elements, right? Cardinality of this is n square plus 1. So this is LD. This is this set. The set is linearly dependent. Why? Because LVV, sorry, LVV, dimension of LVV was n square only. Okay? So this was LD. So there exists some polynomial which will satisfy. Okay, there exists some polynomial like there exists some non-constant AI such that an power tn. Okay, do not also write I here. I I from 0 to n square. This is 0 for some AI non-zero. This is how now what is polynomial? You can directly guess. Fx is equal to take fx is equal to summation ai x power I from 1 to n square. Okay, so this is how it was done. Next is set of all these polynomials which annihilates t, or I should say we satisfy t in this sense. Okay? The set of all polynomials which satisfy it. I should write such that f of t is equal to 0. This is an ideal of is an ideal of fx polynomial algebra. Okay, so polynomial algebra this fx is PID. Okay, so this ideal is generated by some p. This ideal is generated by
What
some.
what is the meaning of ideal something?
Okay, some p. Let me write it. I will write it again. Some px in that ideal, let's I. Minimal. This is minimal degree polynomial. Okay, this is minimal degree. I'm going to explain. This is this is minimal degree polynomial. In ideal is something ideal. Okay, let me write definition. Ideal in a ring, a subset I of subset I of any ring. Here it is of fx, so I'm writing fx. Such that uh, I is subgroup. First of all, I is I with respect to plus is subgroup of fx. This is first condition, and second, for any p belonging to fx and a belonging to I, we have a belonging
AT
to I.
belongs to I. AT or TA belongs to I.
Correct. So because it is commutative ring, so I'm writing ta. You can write at also, doesn't matter. But this is I is basically closed under scalar multiplication of external is scalars are coming from fx. Whatever multiply by p elements of I, they will be lying in I only. Okay. So once f satisfies t in this sense, any multiple of f will satisfy t. Okay. Any rf x, this will be rx fx. This is rx fx. Or this will be r. If you put like t here, apply on t, so rt ft, but ft is 0, so everything becomes 0. Okay, this is ideal. So this is an ideal. So fx is principal ideal domain. This is the fact. I'm not going to show. This is principal ideal domain because of Euclidean. This is also Euclidean domain. I'm not showing that. So this is principal ideal
Constant
domain.
f of x is a field.
No, no. F is a field.
Capital F
Fx.
of x.
Yes. This is not field. F was field. This is polynomial algebra. Fx is okay. Fx is this set. A0 plus an x or n. An not 0. N belongs to natural number, and all ai's are in field F. This collection is Fx. There exists some okay. So this is under plus operation. You know how to add polynomials, how to multiply polynomials. So with those operation plus and dot, this is algebra. Okay.
Okay, sir.
This is ring. This is algebra over F. Let's say. This is also vector space over F. This is ring. That is why it is algebra over F. Okay. As a vector space, it is generated by basis 1, x, x square, and so on. Right. If you understand Fx as vector space over F. So this is not done in the class. I should be very focused. So this minimal polynomial which is generating this ideal, okay, ideal annihilating t, this minimal degree polynomial which is generating, this is called minimal polynomial of t. Okay, here t dx is called minimal polynomial annihilating t, but minimal polynomial of t. Okay. So this was definition for minimal polynomial. Next, it was discussed that roots of minimal polynomial. Okay, P always Px or P always denote minimal polynomial. Okay, in this session, minimal polynomial. Roots of and fx or f denotes characteristic polynomial. Roots of P, this collection is same as roots of fx. So after this, Cayley-Hamilton theorem. Cayley-Hamilton theorem is okay. Let P be a linear operator on V, which is finite dimensional vector space, over F. Okay, some field F, and FB and FB characteristic polynomial. Then F sorry, FD is zero. This operator is zero. F means characteristic polynomial annihilate P. So once F belongs to the ideal, this implies F belongs to the ideal initially, which ideal was discussed, which is just all multiples of P only generated by P, right? P is minimal polynomial. So in particular, since this implies P divides F, so minimal polynomial divide characteristic polynomial. All minimal roots of minimal polynomial is subset of roots of F. So this inequality is proved. Other inequality is similar. I'm not going to solve. This is this follows follows from below theorem. Okay, so this was characteristic. Sorry, Cayley-Hamilton theorem. It was discussed. Whole proof was discussed. I'm not going to prove it, but I wanted to mention this. Okay. After this, that we were suffering that characteristic polynomial of matrix AB, characteristic polynomial of AB is the same as characteristic polynomial of BA. This was proved in the class. Okay, and this is not true for minimal polynomials. Minimal minimals polynomial AB not equal to minimal of polynomial of BA. Okay. There was a counter example given like a is equal to 0 1 0 0, b is equal to 1 0 0. This was a counter example, right? Okay, so next thing was discussed about invariant subspaces. Okay, last two lectures in this week were about invariant subspaces. T is a, as always, T is a linear operator on B. Let T be linear operator on B, which vector space over F. A subspace a subspace W of V is T invariant. T invariant if for every W, small w belonging to W, we have T W which also belongs to W. In other words, same thing, T of W is contained in W. Okay. So here T be a linear operator. This means T is mapped from V to V. Okay. It is linear transformation from V to V. So some subspace W is called T invariant if TW is contained inside W. So various examples were given. Some examples I'm also going to write here. 0, which is trivial subspace, whole subspace V, and any eigenspace. Eigenspace corresponding to an eigenvalue of T. These are some T invariant subspaces. Uh, or भी है kernel T. Okay. Range space of T. These are some T invariant subspaces. Uh, the counter example were given like this. If your matrix representation of T is, let's say, okay, this is, let's say, first. Second is about counter example. Let T is from R2 to R2 and T is given in this form with respect to some standard basis or some basis like this 0, 1, minus 1, 0. Then only R2 and this subspace 0, 0 are T invariant. No other subspace is T invariant. This is some kind of counter example in dimension 1. Okay. In that sense, I was talking. Only these two subspaces are T invariant. Okay. So some exercise were given like if P and U are linear operator, P, if ut is equal to tu, P and U both are linear operator, then kernel U and range U are T invariant. I think some part of this was given to uh, have some exercise. I suppose you have done. If you want, then I can go. Okay, for you exercise. This was given in exercise. So after that, definition about three conductor was given. Okay, if W is some subspace of that. Okay, I'm writing here. Let W be proper subspace. Proper subspace. No need to take proper, right? Okay, a subspace of V. Then and take and take alpha, alpha in V, some vector in V. Then we note this STW alpha this set of polynomials x belonging to P, this polynomial algebra fx, such that Fe applied to alpha, this belongs to W. Okay, this is non-empty service. This subset is non-empty. Can someone point out why?
Alpha belongs in W.
What?
Alpha belongs in W.
No, not necessarily. W is proper subspace, let's say. So I'll take alpha outside W. So you wanted to say take F to be just one. One belongs to STW alpha. No, no. This is pro- this is true if W is equal to V. Otherwise, not. If W is some proper subspace of V and take alpha in outside. Sorry, outside W. Then your argument fails. We just discussed about minimal polynomial. Minimal polynomial of T. What happens for minimal polynomial of T? P, Pt is equal to 0, right? Because P is the minimal degree polynomial, monic polynomial, which annihilates P. This is the generator of that ideal initially. Okay. Initially, we discussed about this ideal. So Ft is sorry, Pt is equal to 0. You want something else? You can take characteristic polynomial by Cayley-Hamilton theorem. Ft is equal to 0, right? So these two polynomials anyway belongs to STW alpha, because once you apply Pt on alpha, means 0 on alpha, it will become 0 and 0 belongs to W. So these two polynomials anyway belongs to. So this is non-empty, okay? And this is also vector space, vector subspace. This is STW alpha. This is subspace of Fx. Okay? So field is always S. This is subspace. Moreover, this notation is for subspace. Moreover, this is an ideal. This is an ideal. Ideal of Fx. Fx is algebra. Means this is vector space also. This is ring also. You can multiply vectors. Means you can multiply polynomials. So this is ring plus vector space. So in vector space sense, this is subspace. In uh, ring structure, this is an ideal. Okay, this is an ideal if I forgot to write. If W is T invariant. Why? Because if Ft applied to alpha, alpha is always let's say in V, Ft applied to alpha belongs to let's say W, then any multiple of F will be also in W. Why? Let's say R into F we are talking about. We want to see if this also belongs to ST W alpha. So this is our question mark. Then if we will use this condition, W is T invariant. Okay. So once something is in W, if let's say small w is in W, then p power 0 applied to W, p W, p square of W, these all belongs to W only. Their linear combination, they will also be lying in W. So something lies in W, then any polynomial, uh, I should not write P, let's say G. Any polynomial G, GT, GT applied to W, this will also belong to W. Okay. So use this fact. Now think about RF. R into F applied to T, and that applies to W. No, no. That applies. Let's say we have taken alpha in V. We are talking about this set. This set is called conductors of alpha in W. So apply it to alpha. This will become R, RT. Here we have FT. Alpha. But FT alpha is belongs to W by definition because F is in STW alpha. Okay. So now use this star calculation. This implies RT, FT, alpha. This belongs to W. This implies R into F belongs to ST. W. Any multiple of F also belongs to this set STW alpha. So this is an ideal of Fx. So this is also principally generated, right? Because Fx is principal ideal domain. So minimal degree monopolynomial which generates STW alpha is called P-conductor P-conductor of alpha in into W. So any T conductor will divide minimal polynomial, right? Remark: any T conductor divides minimal polynomial. You want to see it how? Because P which is minimal polynomial, P belongs to STW alpha, and this is T conductor is, let's say, this is given by this. This is generated by some polynomial. Let's say H. This is because this is an ideal, so it is generated by some single element. So let's say it is S. So P is multiple of S. This will imply P is equal to some H into K, and this implies H divides P. Okay, or some A in Fx. So okay, so this was a remark. Uh, if W is okay, one more thing write here, and then we'll go some solve some question. Okay, let writing here. W be a proper invariant, P invariant, subspace. G when by extending a basis of W to V, let V be extended basis, the basis of W. Then matrix representation of T with respect to this B is of this form: P Q R 0. Okay, where P is let's say proper means some dimension R which is less than N. N is dimension of V and R is dimension of W. Okay, then this is P is R cross R matrix, and these are N minus R. Sorry, yeah, N minus R plus R
n
cross
minus
N
r
minus
cross r, n minus r cross r, and r is the n minus r cross n minus r.
this is some representation. Think about this. It is R cross N minus R. Okay.
Sir, sir, q should be n minus r cross r.
Okay. If you have M cross N means what? M rows, correct, and N columns, right? What is the form of this matrix? 0, 1, 2, 3. This is 1 cross 3, right? Sorry, 4. So this is number of rows here is number of rows here. So R rows here will imply R rows here. But number of columns are different. This is something like you have a square matrix here, and you will have some maybe bigger or lesser, some
Yes,
different.
sir. Yes, sir. I
So this
understand.
okay.
I got it.
So I'm creating this discussion. Okay, so this is good to see. This calculation will help that if we restrict our T on W, okay, if you then continues. Last discussion is continues. If you restrict T on W, then it is a vector, sorry, linear transformation from W to W. Okay, because image is anyway going to going inside W because W is T invariant. T invariant. So now minimal polynomial and characteristic polynomial of this restriction map. Let's say I'm denoting by S P prime minimal polynomial of S uh, F prime characteristic polynomial of S. Then P prime divides P and F prime divides F. The matrix representation in this type, this helps for this conclusion. Okay. Okay. So this is all about classes discussed in the class. Okay. One more thing was left about triangulation. We have enough time, right? No, we have enough time. So, what are triangular operators? Operators. If, let okay, first of all, let T be a linear operator on V is triangular if there exists some basis, there exists basis of V such that matrix representation for T with respect to this basis is some upper triangular or accordingly upper or lower. Okay, upper 0 here. Everywhere below diagonal, everything else in below diagonal is 0. Okay, these are some non-zero constants. Maybe non-zero. Maybe non-zero. Okay, so these kind of P are called triangular operators. Okay, so some operator is triangular or not. To check that, uh, what we do is we see some lemma. Okay, this lemma will help to get matrix representation in simpler form, like this triangular form. Okay, a lemma would be a linear operator on a finite dimensional vector space. Finite dimensional, we have already taken this convention that all the vector spaces are finite dimensional. So let T be a linear operator on a vector space V over a field F. And P, which is minimal polynomial, this is also by convention denoted by P for this session. So P is of this form x minus C1 over R1 into x minus CK or RK. C factorizes like this over a P minimal polynomial and WB is a proper subspace of V. WB, okay, every time and then not good. Minimal polynomial of T. Let W be a proper subspace of V, then first is there exists some alpha outside, there exists alpha in V but not in W. Alpha not in W such that for this alpha, particularly this alpha, this is like T minus Ci applied to alpha. This will belong to W. Means this linear polynomial means x minus c will work as T conductor of alpha. Okay, for some characteristic value Characteristic value of C of t. This C is characteristic value. C is the characteristic value. So do you want to see this? Because I suppose the last 1 hour will be enough for question answer session. So let's see this lemma was how it was. Okay. So we already see above that any T conductor divides minimal polynomial. This remark. Okay. So here we are looking at this polynomial which is x minus c. This is T conductor, right? So whatever we don't know yet, some T conductor F, we denote it by H. Sorry, H. H divides F. Okay, H is the T conductor. H is T conductor of alpha in W. Then H divides F by remark. So H will be of the form. H will be of this form. X minus C1 power E1, and last is X minus CK power EK. So H is the minimal polynomial for which HT of alpha belongs to W. It is minimal degree polynomial. Okay, so keep it in mind. Later we will use this fact. So H is like this. So I would like to say all EIs are not zero. Some I'm saying some EI is not zero. Why? Otherwise, what will happen? H is equal to 1. Okay. Once H is equal to 1, then what this condition implies? This implies alpha belongs to W, and we want this will be the contradiction to the first one. Okay, we are taking alpha outside W, so this is why some EI is non-zero. Let's say I'm going to write E1 is not zero without loss of generality. Why I'm saying without loss of generality? It can be anything, but after because fx is commutative ring, so these factors we can write in any order. Okay, order does not matter. That is why. So let's say E1 is non-zero. Let E1 is not equal to zero without loss of generality. Then think about this polynomial. I'm writing it by gx, which is just x minus c1, e1 minus 1, x minus c2 power e2, and so on, x minus ck power ek. Its degree will be lesser than degree of h, right? Because x is equal to x minus c1 into gx. So degree of gx is less than degree of hx. Correct. So this is certainly true that gt alpha will not lie in w because h was the smallest degree polynomial and g is lesser than degree of h. So this does not gt alpha does not belong to w. Okay. So update your alpha. This alpha was already outside. Okay, this particular alpha we are talking was we have taken outside W. Now this also lies outside W. Let's say we are writing it by alpha prime for time being, Uh, or at I will rewrite the theorem. Okay, write it as beta. What will happen now? H e is equal to p minus c 1 I g t, right? Apply to this alpha, initial alpha. Okay, this belongs to W, but GT alpha, this does not belong to W. So we got this T minus C1 I applied to beta belongs to W, and beta does not belong to W. So now you can take beta is equal to alpha. Everywhere initially we taken was alpha prime, for example, right? Uh, Alpha prime. Let me write here in other color. Take alpha prime belonging to B but not in W, and T is that H is T conductor of alpha prime. Okay, then all these arguments is similar, same in fact. So now by taking this alpha equal to this beta is beta is nothing but gt applied to alpha prime. So we got this is last argument. This is second. This is first. Okay. Any question here? No question. Okay. No, we have no slide. We got question number one. P and U be linear operators on V such that PU is equal to UT. Then which of the following statement is correct or correct? Range of U is invariant under T. This is true, right? This part is done in the class anyway. But null space of U is not invariant of T. This is wrong. Range of U Least ways of u both are invariant under T, discussed in the class. Range of T is invariant, but range of u is not invariant. Range of T is invariant under T, right? This is true. Range of T and kernel of T, these two things are invariant under T. Now about u is given. Range of u is not invariant under T. This is false. Right? Range of u and null space of u, they are both also T invariant. So this is false. Same logic discussed in the class. Range of u is invariant under T. Okay, this is true. But null space of T is not invariant under T. This is false. Null space of T, range space of T, both are invariant under T. This is also false. Range and null space of T is invariant under U. This is discussed. Note that extra thing that kernel T, range T is a T invariant. An exercise was given about this uh, kernel U, range U, these are also T invariant. So let's see second question.
Option D is correct, sir.
Yes, option D is correct. Option D is correct. So let's see second question. Let T be a linear operator on a space of all polynomial functions degree less than or equal to 3 given by this relation. Then this is projection onto second and fourth coordinate. Matrix representation of T with a standard basis. Let's say B is equal to 1 x x square x cube. Then what is TB? Okay, how to write it? Where 1 goes to 0. So first column becomes 0 column. Where x goes, it will go to just x. So you just get 0 1 0 0 because x is in the second place. So you got second coordinate 1, all other coordinates 0. Where x square goes to 0, by this equation you just directly look. X square goes to 0, so third column becomes 0. Where x cube goes, x is just x cube. So only fourth coordinates become 1, every other 0. So this is your matrix representation of T with respect to a standard basis. So what is characteristic polynomial of T? Is what? Someone tell by looking this matrix. This is just x square and x minus 1 uh, square. Okay. So first option is correct. Okay, this is confusing. This might be confusing that either it might be in a plus or minus, but does not matter. After all, every time we work, becomes a equation, characteristic polynomial. What is equation? Characteristic equation, and roots are not going to change. So this is good. So this is also characteristic polynomial. Okay, that is a minimal polynomial of this. So first of all, characteristic polynomial and minimal polynomial, they share roots. So minimal polynomial should be multiple of x minus x into x minus 1, right? Because roots of minimal polynomial and roots of characteristic polynomial are same. So 0 and 1 are roots of characteristic polynomial. So 0 and 1 should be root of minimal polynomial. So this should uh, this might be true because this is multiple of this thing. But if this is minimal polynomial, degree is minimal, right? Here. So this will be minimal degree polynomial, minimal polynomial, and this will fail. So let's check about this. So I'm saying minimal polynomial of t is x into x minus 1. My matrix representation of x is like this 0, 1, 0, 1. Everything else is 0. What is t minus 1? Means, sorry, minus 1. It will become t minus I. So t is given, minus I means minus 1 here. It will become 0. Minus 1 here. It will become 0. All other entries are 0. So if you multiply two diagonal matrix, corresponding entries gets multiplied. So first diagonal entry will be 0 into cross minus 1. Second is 1 cross 0. Third is 0 cross minus 1. And last is same 1 cross 0. So this becomes 0. Okay. So this is enough. This is minimal polynomial. And this is not because of the fact this is bigger in degree. So this fails. This is incorrect statement. E is not diagonalizable. Let's see if T is diagonalizable or not. Eigenspace corresponding to 0 is corresponding to 0 value, eigenvalue 0 is span of 1 and x square. These two things are only going to 0, right? Just look at basis elements. 1 and x square are going to 0. What about x and x cube? There, x is going to x and x cube is going to x cube. So kernel corresponding to this 0 eigenvalue of t minus 0 I is kernel of t only. This is kernel of t only. And this is nothing but a span of 1 and x square. And this is two dimensional, right? Very nice. We got two eigenvalues.
How you
Sorry.
got the eigenspace one or x square? Another G.
Okay. So you understand this. This is eigenspace corresponding to t, as kernel of t minus 0I. 0I is nothing. It is equal to kernel of t. 0 does not do anything. So this is just kernel of t. Now kernel of t, look at basis 1 x x square x cube. 1 is going to 0, x square is going to 0, and x is going to x, x cube is going to x. So kernel is clearly spanned by these two vectors. These are linearly independent. What is range of t? Range is two-dimensional. Means rank is just two-dimensional. Sorry, rank is 2. So kernel of t should be What is nullity of T? Nullity of T should be 2. So we got two vectors in kernel, linearly independent. So that will imply that 1 and x square, they are enough to span kernel. No extra requirement to extend the basis. So this is enough because nullity is 2. Rank nullity theorem. Use rank nullity theorem. Okay? This is clearly, this is clear. You observe this and you will get it. So eigenspace corresponding to 0 is spanned by two vectors. It is two-dimensional. So we got two eigenvectors. If it is diagonalizable, we should get two other linearly independent eigenvectors. Then only it will be diagonalizable, right? We should have a basis. It consists of four elements. All four should be eigenvectors. So we already got these two, 1 and x square. These are eigenvectors. Okay. X and x cube are also eigenvectors. Why? X and x cube are eigenvectors corresponding to 1. Corresponding to e value 1. Okay. See, look at these two things. T of x is equal to x, T of x cube is equal to 2. So this is basis basis consisting of eigenvectors. So T is diagonalizable, but what it says is not diagonalizable. So this should be wrong. Okay.
So, what is the condition for diagonalizable?
We should get a basis. All basis elements would be eigenvectors of T. This is definition of diagonalizable. Right? We are going by basic thing. T is diagonalizable provided we should get a basis and all basis elements should be eigenvectors. Because in that case, let's say e1 e2 en is basis and you are writing like t1 t e1 is equal to lambda 1 e1 and t en is equal to lambda n en. So what is matrix representation of t with respect to this ei basis? It's diagonal matrix, right? Lambda 1 lambda 2 lambda n.
Say, eigenvalue should be non-zero. Is it correct?
No, not necessarily. It could be zero also.
Okay, sir. Then
If all these
how can you decide whether it is not diagnosable? If it is not diagnosable, how it should be?
uh, to prove it is not diagonalizable, uh, it is very easy. Okay, first of all, you calculate eigenvalues. If eigenvalues does not exist in your field, you directly say this is not diagonal.
Oh,
First of all that eigenvalues should exist, and corresponding to all eigenvalues, you should get eigenspaces,
Eigenvectors.
eigenvectors.
Eigenvectors should be the basis of the diagonalism.
okay, sir.
Enough eigenvector, I should say. You might get one or two, but you should get n eigenvectors. Okay, then only it will become basis. Okay. So what about D? Let me stop it, or let it be written. Algebraic multiplicity of 1 is 1. Look at this equation, characteristic equation. What is algebraic multiplicity of 1?
Wrong, sir, wrong. We have 2. Algebraic
So,
multiplicity of 1 is 2.
correct. What is geometric multiplicity? It is also 2, right?
Sir, but here in the option, it should be, it's written as 1.
This is anyway, this is wrong. Algebraic multiplicity, I agree. This is 2. Okay, this is algebraic multiplicity of 1. But what about geometric multiplicity of 1? Geometric multiplicity is nothing but dimension of this kernel of.
Nullity, dimension of nullity.
I should have asked about 0, but anyway, geometric multiplicity is nothing but dimension of
Dimension of subspace, sir.
kernel of t minus I. This is nothing but spanned by this is 2. Why? Because geometric multiplicity of 1 is dimension of this. This is 2 because uh, since kernel of t minus I, this is nothing but span x x2. Okay, so this is 2 dimension. So geometric multiplicity is 2. When all geometric multiplicity and algebraic multiplicities are equal, corresponding to each eigenvalue, then only T is diagonal eligible. Okay. Okay. Let's see next question. I suppose you understood.
Sir, then D option is wrong, no?
Yeah, yeah.
You have to tick correct.
Oh, sorry. This is why you are pointing out.
Yes, sir. That's why
Okay.
I am.
Sorry. Let's see third question. Let V be a finite dimensional vector space for F. Dimension is n. Then minimal polynomial of zero operator is x for n. What is zero operator? It will get a matrix representation of this form. Let me write it sada n cross n. Okay. All elements are zero. What should be its minimal polynomial? Minimal degree polynomial which satisfies this matrix
Should be 0.
x, right? Why x? Why zero degree polynomial does not satisfy this? Zero degree polynomial will be of this form. One, maybe one. Okay, let me write one only. One will never satisfy any polynomial. If you put any operator t on it, it will give one only, constant one, right? One is constant polynomial. If you give me x minus one, when you apply t on it, it will become t minus I. Okay, it will become I, sorry. 1 applied to t becomes 1 into I. So, no constant satisfies this t, but x satisfies this. X of t will become t, just t. X square of t becomes x t square. So, but t is anyway zero matrix, right? Zero operator. X only satisfies. So, this is higher degree term. I'm not going to calculate higher degree polynomial, which annihilates t. So, one is x and x annihilates. How to guess it? Why it should be x? What is characteristic polynomial of A or zero operator. Let's say write it Z, characteristic polynomial of Z. This will become x power n, right? But roots of characteristic polynomial and minimal polynomial are the same. So it should minimal polynomial should be x power some I, right? But x power n only in one n relationship, so no need to see uh, higher degree x power I. Okay, understood?
Yes, sir.
That means in this case, characteristic polynomial and minimal polynomial both are same.
No, I'm saying roots of them are same. Roots, collection of roots of minimal polynomial and collection of roots of characteristic polynomial, they are same.
Okay, okay.
Okay, so minimal polynomial of identity operator is this. This is wrong anyway. This is similar by same thing. Look at x minus 1. This is minimal polynomial of identity. Okay? No need to go for higher order x minus 1 power something. Because once you apply identity on it, it will become identity minus identity. And this will become 0. So x minus. What about C option? C option is minimal polynomial of 0 operator is x. This is correct. Minimal polynomial of identity operator is x minus 1. This is the understood, right? This discussion. I'm going to next question. I suppose you understood. Let P be linear operator on F3. Matrix representation of P is this. Okay. Then uh, these equations, if you look like see these equations, so this might be talking about characteristic polynomial, Cayley-Hamilton theorem, right? So let's see what is characteristic polynomial, and this might be talking about these two minimal polynomial, right? So first of all, let's say let's calculate characteristics polynomial, then see which option is correct or which is not. So determinant of a minus xi. This is determinant of minus x 0 1 1 minus x minus 3 0 1 3 minus x. This determinant, let me see attendance, how many of you are attending. We are 18 numbers. Okay. Determinant of this matrix. So let me expand this. You can help me if I'm doing wrong. Point out those things. 3 minus x plus 3 plus 1, right?
Correct, sir.
So this will become, and let's multiply all this, minus 3x plus x square, sorry, x square plus 3 plus 1. Now multiply by minus x cube. It will become, sorry, minus x cube plus 3 x square minus 3 x plus 1. So you, if this is not matching, you can take determinant of xi minus a, and this will become x cube minus 3x square minus, it will become plus 3x plus plus will become minus, sorry. Okay, right. So which option is correct? Look at this. Once A is correct, this fails. Right?
Yes, sir.
And what is this characteristic polynomial? If I am not wrong, this is x minus 1 to the power 3. Am I correct?
Yes, sir.
Okay, then what minimal polynomial can be?
X minus
Let-
1.
X minus 1.
Minimal polynomial uh, can be x minus 1 or x minus 1 square or x minus 1 cube, right? Or only one of this, which is minimal degree, that will become minimal polynomial, right?
Yes. Yes.
So let's see. So D is anyway going to be incorrect because this is not neither x minus 1 nor x minus 1 cube nor x minus 1 square. So D might be correct, but we don't know yet, right? D might be correct. This is question mark. Let's see. This is nothing but x minus 1 to the whole square, right? Okay. So what is A matrix? 0, 0, 1, 1, 0, minus 3, 0, 1, 3, 0, 0, 1, 1, 0, minus 3, 0, 1, 3. Okay, so this is your A matrix. What I'm going to do is minus I, x minus I is 1, 1, 1 to the whole square. First of all, let's calculate this is your x minus, sorry, I should write t minus I. Now then we will calculate if t minus I square is 0 or t minus I is 0 or t minus I cube is 0. Let's see. T minus 1 is this matrix represent. I'm just writing matrix representation. This is minus 1, 0, 1, 1, minus 1, minus 3, 0, 1, 2. This is not 0. So t minus 1 is not a minimal polynomial. Means x minus 1 is wrong. This is not minimal polynomial. So what about t minus I whole square? So t minus I is already written here. So this is minus 1, 0, 1, 1, minus 1, minus 3, 0, 1, 2. We are going to square it. So this is minus 1, 0, 1, 1, minus 1, 3, minus 3, 0, 1, 2. Multiply them and what we get? 1 here, 1 here, right? Are we getting 1 here? Right? We are getting 1, right? This is anyway, we just checked one entry. This is not 0. We got it, right? So this is also not minimal polynomial. Only possibility is that this is minimal polynomial. So this is minimal polynomial. And we got that answer B is infinite. Okay. You understood or not? Okay, I suppose you understood. So let's see next question. We have 4 × 4 matrix. And which of the following statement is correct or correct? One is an eigenvalue of this, 0 is an eigenvalue of this. Characteristic polynomial and minimal polynomial of A. So first of all, let's calculate uh, characteristic polynomial of A. That is the easiest part about B. So we have 4 × 4 matrix because this block is 0 0. This will help doing calculation. Okay. So we will expand our determinant along this column because this column is the good, right? Helpful. This will help in expanding things, right? Correctly. So let's do. So first of all, characteristic polynomial is determinant of xi minus a. So this will be determinant of x minus 1 minus 1 0 0 1 x plus 1 0 0 here minus 2 minus 2 1 1 2 minus x, sorry, x minus 2 minus 1, where we have 1, here we have x. So this is what it is. Let's expand as usual. Okay. X minus 1 with this determinant of this matrix x plus 1 0 0 minus 2 minus 2 1 1 minus 1 x, and then plus 1, and like for this determinant of 1 minus 2 1, we will leave these entries on this column as well. Okay. So here we have 0 x minus 2 and then minus 1 again 0 1, this is 1 x. Good. Now we have easy part, x minus 1. Now expand along first row, then it will become x plus 1. Now it is x square minus 2x plus 1 plus determinant of this will along first row, if you expand it will become x square minus 2x plus 1, right? So this is common in both. So take x square plus 2x, sorry, minus 2x plus 1 common. What left inside it? X minus 1 into x plus 1 plus 1. This is left. So this is x minus 1 to the whole square, and what left inside is write it x square minus 1. Okay, this product is x square minus 1. So plus 1 is x square. So this 1 and minus 1 get cancelled. So this is nothing but x square x minus 1 square. Okay, so we see that D option is incorrect. Okay, characteristic polynomial is not what we were expecting. We got something like this. You understood? So D is incorrect. We understood. What about minimal polynomial? Now, possibilities of minimal polynomial, looking at characteristic polynomial, what we have possibilities? X into, it should be first of all multiple of x into x minus 1. Okay. Now, not every multiple of this, just x multiple or x minus 1 multiple of this. So this is first possibility. Second possibility, it could be x square x minus 1. Third is that characteristic polynomial itself minimal polynomial. Okay. So let's check by one by one. So smallest, this is the smallest degree. So we should start by smallest degree. For smallest degree possible polynomial. So this is smallest degree. Let's say, help me writing out matrix. What is x? It is 1 1 0 0 minus 1 minus 1. Okay. Let me see if I can write it. I can remember this matrix or not. -2 -2. I forgot to. Sorry. -2 -2. 2 1. Here we have 1 minus 1 0. Right. So this is your matrix A. Now you have matrix x minus identity, means A minus identity. So this first will become 0 1 0 0 minus 1. Now extra minus 1 will be -2 0 0. Entries are changing only in diagonal. You see it correctly. -2 -2. 2 will become 1. We are subtracting it in the diagonal by 1. So it is just 1 1 1 -1. Here we get -1. This is your p p minus I. So let's see if it is 0 1 1 0. So first entry we get is -1. This is clearly not 0. We get 4 cross 4 matrix, and this is not 0 because first entry is 1. So this is also wrong. C part is also wrong. So no need to calculate minimal polynomial anyway. So 0 is an eigenvalue of, and 1 is an eigenvalue of this. So let observe one thing, that if lambda is an eigenvalue, is e value of t, then there exists some non-zero v. There exists
Sir,
v. Yes.
x into x minus 1 whole square will not be minimal polynomial.
Yes, this is not minimal polynomial.
X into x minus 1, x square into x minus 1, x square into x minus 1 whole square. What about x into x minus 1 whole square? Will it not be minimal polynomial?
Oh, sorry. This is also possible, right? Uh, Thank you. This is also a possible choice. It
Okay, sir.
can be.
Okay, sir. Thank you.
Uh, if we're just looking at first, it is not an minimal polynomial.
But we
So
must check. We must check.
yeah, you can check, right?
Okay, sir.
If it is necessary, of course you can check. Okay. This is an observation I'm writing for next. Observe that if lambda is an eigenvalue of t, then there exists some non-zero v in capital V such that PV, sorry, this is diagonal. Then there exists some non-zero V such that T V is equal to lambda V. Okay. Then what about T square V? Lambda is also eigenvalue of T square or not? Let's see. By this line, we are looking at linear operator T square. I don't know what lambda square or lambda what is eigenvalue or not, but of course we get T EV like this, and but TV is lambda V, right? Lambda V. So you get lambda outside T, right? Because T is linear operator. So this is just TV. Again TV. So you get lambda into lambda V because TV is lambda V. Use this star. Okay, good. So you get lambda square V. So once you have lambda is eigenvalue of T, you get lambda square eigenvalue of T square. Okay, right? In particular, if you have any polynomial et applied to V, it will become P into, sorry, P applied to lambda into V. This was a lemma proved in last week, last week, right? Fourth or fifth week, right? With the same eigenvector, right? So P lambda is eigenvalue of Pt. So remember this. So here, in this case, first of all, note that 0 and 1 are only eigenvalue of E values of P or A. Here I should write it. Okay. So what is this polynomial? This polynomial got 2 this 0 square plus 5 5 into 0 plus 3, and this is 3. This 3 is okay. Put 1, you put 1, this will become 1 square minus 5 plus 3, and this is minus 1. So you just get 3 and minus 1 as fruits. Sorry, eigen values of A.
Again,
Eigen values of this matrix. Sorry. So that was a small observation, but it applies this. If you get a some linear operator, and that linear operator has only eigenvalue lambda 1, let's say one eigenvalue lambda 1, then any linear combination or polynomial like this that will have only one eigen uh, value, but that will be p lambda. If you have initially lambda for A, then you get p lambda for this matrix PA. This is if you PA. Okay, so this is observation. You can prove it if you wish. So first option is incorrect. So what about B option? 0 is an eigenvalue of this matrix. Let's check. So 0 square plus 2 into 0 minus 3. So for this is This is nothing but minus 3. What about 1? 1 square plus 2 into 1, matlab 1. Sorry, 2 minus 3. Oh, nice. This is 0. 0 is an eigenvalue of it. Everyone understood? So I can go next question. This is the explanation for A. This is for B.
So if you substitute 0, it's not getting 0. Only
Yes,
1
if you
substitute will get 0. Then
correct corresponding to
0 is
1, you
eigenvalue at telling, sir.
what?
0 is eigenvalue.
Correct. 0 is an eigenvalue.
How, sir?
We have eigenvalues 3 and 0. Two eigenvalue for this, right?
Uh-huh.
3 and minus 1, 3 and minus 1, two eigenvalue for this.
Okay.
So this last line is explanation to this. Okay. Okay. I suppose you understand. So let's see next question. I'm not prepared for this. So there might be some question which I will leave today, but we'll do in next session if I got it started. Okay. So A is let A be n cross n real matrix. That means real entries. We have 15 minutes. Let me do fast. A B n cross n real matrix, which is correct statement. Or n is equal to 4, or n is equal to 4 is not similar to a triangular matrix. If A is not similar to triangular matrix, then A is similar over C to a diagonal matrix. Uh, I think this is not true. Okay. Take example, for example, this matrix. Okay. 0, minus 1, 1, 0. This will give in characteristic polynomial. This will give what x square minus 1 factor as a factor, right? X square plus 1, which is not factorizable over R. So this is not similar to a triangular matrix over R. So first hypothesis is satisfied. Why this is not triangularizable? If it is this matrix I'm going to write is triangularizable, all eigenvalues should be in R because all the diagonal entries, these diagonal entries are eigenvalue in just that upper triangular matrix case, all the diagonal entries are eigenvalue. Okay, so this is okay. I'm creating a matrix right now. 0, 0, 0, 1, 0, 1, 0. Is it triangularizable? Sorry, diagonal matrix. Of course not. Why? What is characteristic polynomial of this matrix A? This is not triangular. Okay, this is not similar to a triangular matrix. And what is characteristic polynomial? I'm showing this is wrong answer. Why? You get characteristic equation x square plus 1 into x cube. This is for A. Sorry. This is just x square. Right. So you get three eigenvalues. E values 0, I, minus I. Right. 0 has algebraic multiplicity 2. Algebraic multiplicity of 0, this is 2. We should get geometric multiplicity equal to 2. Question mark is here. Is it true or not? If it is true, then it is diagonal matrix. I'm saying, I'm giving a counter example. This means this means this is not a good counter example. Okay, so I'm saying this is not geometric multiplicity of 0. How to calculate? This is equal to, I'm writing here, gm of 0. This is dimension of kernel of t minus 0 t minus 0 but this is equal to dimension of kernel of t, right? What is rank of this matrix? Can you say directly? Rank of A is rank of A.
Three,
Note that,
sir, three.
correct, rank of T or A, whatever. This is 3. So what is nullity of T?
N minus 3.
One.
This is 1, right? So kernel is one dimension. Kernel T is just 1. So we got not equal things. In symmetric multiplicity of 0 and algebraic multiplicity, they are not equal. So this is not diagonal algebra. So this option is incorrect. If n is equal to 3, n is not similar to a triangular matrix, then is similar to diagonal matrix. Yes, over C it is correct. How to see this? Deeper. You have 3, n is equal to 3. So any 3-degree polynomial has a real root. So characteristic polynomial fx has a real root. This is very important. It, it is, you should remember this. This is coming from analysis. Okay, fx has a real root. So if it is triangular, all real roots are in the diagonal, but it is not triangulable. Triangular, it is not triangularizable. इसका meaning ये है कि fx is of this form. Fx is something x minus alpha, which is real number, and something x square plus some positive lambda. Lambda is some or 2-degree polynomial, I should write, which is having no real roots. Okay, over real number, something like this. Then over C, fx got 3 different real eigenvalues: alpha, x minus something, beta, x minus gamma. Alpha, beta, gamma, all 3 are not distinct. Then now from here you can say A will be diagonal as well. Okay? So B option is correct. Minimal polynomial is itself characteristic polynomial, and it is factorizing into linear factors. Linear means 1-degree factors. All factors are in 1 degree. So this is diagonal over C, diagonalizable over C. Or n is equal to 4 is not similar to R, rectangular matrix, or R. And A cannot be similar over C to a diagonal matrix. This is very wrong. A can be similar to diagonal matrix. For example, you take this one, 0, minus 1, 1, 0. This is not triangularizable, but think about this. The extra part which was uh, confusing was this part, this block diagonal, this block, right? Now it is already diagonal, this block. Now for this particular block, you get x square plus 1. Others are just x minus 1 whole square. Other factors in characteristic polynomial. So corresponding to eigenvalue 1, you get symmetric multiplicity, algebraic multiplicity, both to look at this. Okay, but this factor has distinct roots. At least one eigenvalue will give one eigenvector. Okay, so so you get a diagonal matrix, but they are saying cannot be. This is wrong. This is a counter example. This is explanation for C. This is for A. D is equal to, sorry, D says n is equal to 3 is not similar to triangular matrix, then A may not be similar or set to triangle. This is incorrect. Why? Because B is correct. Because we see B is correct. Okay. So let's see next question. So we have 8 more minutes, 8 or 10 more minutes. You understood this? If you do not understood, you can watch it in YouTube. It will be available. So I suggest you can watch it in 2x speed. Okay, because I'm speaking very slow. Okay. Question number 7. Let V be the vector space of n cross n matrices. A be a fixed n cross n matrix. P and U be linear operators on P. That P is given by multiplication by A, and U is given like this. Then A is diagonalizable. Then P may not be diagonalizable. Minimal polynomial of P and A may not be seen. I think I cannot do this right now, but we'll do in next session. And in the next session, what we'll do, uh, we'll recall few things only, so that we get extra time, and we will come back to this question. Okay. With this promise, I'm leaving this question. Okay. Sorry for that. Uh, Look at this matrix. What is rank of this matrix? Clearly, it is 2, right?
Two.
Because first and third column are same, and second and third column are same. Sorry, rows. You can say column also. So you guys just get two independent rows, other two are depending on them. Okay, so this is called a similar or rational numbers to a diagonal matrix. If you have again vectors, okay, characteristic polynomial. What is characteristic polynomial of this? From here, first quadrant, sorry, first block, you will get okay. Could we calculate? Let's calculate characteristic polynomial. X minus 1, 0, minus 1, 1 minus x, sorry, x minus 1, 0, 0, 1, x minus 1, minus 1. Here also minus 1, minus 1, 0, minus 1, x. Determinant of this. You get x, and then determinant of this is smaller. Uh, this is very lengthy calculation. I don't want to do. But assume that 0 and 2 are eigen values. Okay, then look for C. If C is correct or not. You have two eigenvalues. Okay, what is the geometric multiplicity of them? One is for 2. This is also for 2. This is characteristic polynomial. I'm assuming that. Okay, assume, and you can calculate it. Okay, once you calculate, if it is coming this, then all the calculation I'm going to do for C will follow. So you have two rational eigenvalues. 0 and 2 are rational numbers. Geometric multiplicity of 0 is 0 is 2. Why? It is just nullity of A. Rank is 2, so nullity is also 2. Geometric multiplicity of 0 is 2. So it is matching with algebraic multiplicity of 0. What about 2? Geometric multiplicity of 2 is question mark if it is 2 or not, but algebraic multiplicity of 2 is 2. So let's calculate geometric multiplicity of 2. It will be 2 minus 1, 0 minus 1, minus 1, 2, minus 1, 0, 0, minus 1, 2, minus 1, minus 1, 0, minus 1, 2. What is rank of this matrix? And then we'll see what is nullity. Let's do little calculation for this at least. To calculate rank, we'll reduce to echelon form. 2 minus 1, 0, minus 1. Multiply by 2 and add. So what I'm going to do, going to fix second column and multiply by 2 and add in the first. So minus 1, 2, minus 1, 0. So first entry becomes 0 and second entry we are multiplied by 2 in second row and adding to first. So it will become plus 3 and this will become minus 2 and this is itself minus 1 only. It is anyway 0. This is minus 1, 2, minus 1. Now multiply by minus 1 here and add to fourth line. It will become 0. It will become minus 2. It will become again 0. This will become 2. Now we will multiply by 3 here and add in the first row. So it will become 0, 0, minus 4, sorry, plus 4 because it is 6, minus 3, plus 1, minus 2, minus 1, 2, minus 1, 0, 0, minus 1, 2, minus 1, 0. Uh, Again, multiply by plus 2 here, sorry, minus 2 here. Then it will become 0 and this will become minus 4 and last entry will become plus 4. This has rank is equal to 3, y minus a. equal to 3, right? Because this can this after this, and these last two are also not multiple of each other. Right? So rank. Okay. Oh, sorry. What? We are getting rank equal to 4. Really? Rank at least if their two is eigenvalue, so rank should be at least sorry, at most 3, because at least one kernel, one vector which is eigenvector should be in the kernel. So there is some mistake. There is some mistake. Otherwise, 2 will not be an eigenvalue. Okay, let's see if there is easy question. AB 3 cross 3 matrix whose magnitude is what it can be. Looking at this is correct. This is the easiest option, I can say. Checking these things will require um, some mysterious calculation. At least 0 should be an eigenvalue. So, okay, I understand. This is invertible matrix. Rank is 3. Rank is 3. Wow, this is also rank 3 matrix. So it is invertible matrix. So 0 cannot be an eigenvalue for this. Ah, yes, this is also rank 3. Okay, 1 minute. What I'm doing is I'm checking number of linearly independent columns. So they are all linearly independent. I can check directly, but you should check it once more. They are all 3 rank, so they're invertible matrices. No, no right choice for them. So this is only correct option. Okay, check them using this is invertible, and this will imply 0 is not an eigenvalue of it. So x square cannot be can not be minimal polynomial. Okay, so this is why, because product of lambda is, this is determinant of a. Lambda is eigenvalue of a. Eigenvalue of a. Product is over all lambdas. So which multiplicity, यहाँ पर लिख देते हैं multiplicity of lambda. यहाँ पर लिख देते हैं this thing. Okay. Anyway, you will see it later. Okay? These are all 3 rank matrices, so invertible. 0 cannot be limit. What about this one? Our time is over, but I will finish after this question. Okay. Those questions which are left, we'll do in next session. AB incursion matrix with real entries. Which of the following statement is our correct? A square is equal to 0. Then A is diagonalizable over complex numbers. No, this is no. Counter example is I'm giving. Look at this one matrix 0, 1, 0, 0. This is not diagonal, but square is 0. Okay, so this is incorrect. Why it is not diagonal? What is the characteristic polynomial? It is x square, right? So only 0 is an eigenvalue. 0 is e value. What is geometric multiplicity of 0? algebraic multiplicity of 0 is 2, because look at this equation. What is geometric multiplicity of 0? This is not 2, this is 1. Look at this matrix. What is rank and kernel? Nullity is just 1. Nullity is 1, kernel is rank is 1. So geometric multiplicity is 1. A square is equal to I for this. For this I have to think how A square is equal to identity. Okay. I'm saying if uh, A is anyway from V to V. Okay. So I'm saying AB is subspace of V. Image of it is called range. AB is subspace of. If uh, then this is subspace and get a basis. Get a basis of AB. What is basis? U1, sorry, V1, V2, Vk. Let's say it is basis. I'm saying this is all eigenvectors. These are all eigenvectors of it. Vectors of it. How? These are V1 is belonging to AV. This means V1 is equal to some already V of V1 prime, right? So now you apply A on V1. So what you get is A in place of V1, you can replace A V1 prime, but you get A square of V1 prime. There's some mistake. It seems not. A square is identity. So you get just V1 prime. I should get V1. What is condition? There is another way. I was about to get a basis of eigenvectors, but forget about that and think about minimal polynomial. Okay, this is not coming out. What is minimal polynomial of A? Minimal polynomial of A will satisfy x square minus 1, right? Because A square minus is equal to identity, which implies A square minus I is equal to 0. Minimal polynomial is this, then it is factoring into linear factors x plus 1, x minus 1. If you have minimal polynomial which is factoring into linear factors, distinct linear factor, then matrix is diagonalizable. Okay, so this option is correct. Okay, for this, sorry, this will work only for this, because in this case A square is equal to A. You have A square here, you get A, but A V1 prime is again just V1. So this is for C part, but this only thing, this is incorrect. This is true for any field. That is because of that it is false. Because of this only. Why? You get eigen once you extend this to basis of V, all the other extension basis, let's say V a plus 1 and Vn, these are in kernel of it. This is spanning kernel. So these are also eigenvectors, right? With a corresponding eigenvalue 0. So we get a basis of V. So okay, I'm so fast. You might not understand at this time, but let's see. We will do some uh, more thinking in next time if we meet, because time is 10 minutes over after that. Okay. What about D? If A satisfies this equation, A may be similar to a diagonal matrix. This is correct option. Maybe. Even if one example you found, this is true. Just get A is equal to minus I. Take D is equal to, T for D, take A is equal to minus I. Okay. Then minus, if you put A is equal to minus I, this part will be 0. So it will be 0. But A is also diagonal matrix, right? So A may be similar to a diagonal matrix. This is correct. Once more, okay. For B, I just gave minimal polynomial is factoring into linear factors, and they are distinct linear factors. Huh? We will see if I think this was already discussed in the class, right? If minimal polynomial factors into linear factors, then geometric multiplicities and algebraic multiplicities, they are all. I'm not going to explain that, but this C part you can look into internet. This if this condition holds, we say A is idempotent. A is idempotent, and idempotent is same logic applies here also. You see, what is minimal polynomial of this? X square minus x, and this is factoring into linear factors, distinct linear factors. Okay, so idempotent and this kind of matrix where factorization into linear happens, they're all diagonal as well. Why C is false? Just because of this. Only for C. This happens for all in the. So I'm finishing it now. I suppose this is understood. We are leaving this part, question 8 and question 7. नेक्स्ट सेशन में इनको करेंगे. ओके. While recalling, I was doing so much. I should stop early so that questions get enough time. Thank you. We will meet next week. Okay. Bye bye.